The most annoying bugs in C++ are the ones that only happen sometimes. In this video we are going to look at one of the most fundamental problems in C++ systems programming. How to safely pass data between threads. If you've ever tried to use a standard std vector or queue across multiple threads, you have likely encountered immediate crashes or worse, silent data corruption. This happens because the standard library containers in C++ are not thread safe by default. They prioritize performance over safety, assuming that you, the developer, will handle the synchronization. We are going to move through three distinct phases. First, let's look at a naive implementation to demonstrate exactly why and how it crashes. Let's look at our starting point. This is a classic producer-consumer setup, but implemented naively. At the global scope, we have a standard std queue of integers. This is the shared resource. In a real application, this might be a buffer of network packets, log messages, or rendering commands. Its job is simple. It iterates 10,000 times, pushing integers into the global queue. This simulates a high-throughput data source. Down here is the consumer. It runs an infinite while loop. Inside, it checks if the queue is not empty. If there is data, it reads the front value, removes it from the queue using pop, and prints it to the console. And finally, in main, we spawn two distinct threads, T1 running the producer and T2 running the consumer. We then join them to ensure the main program waits for them to finish. On the surface, this logic seems sound. We check if the queue is empty before we pop, so we shouldn't be accessing invalid memory, right? However, this code is critically flawed. When we talk about this code being unsafe, we are referring to a specific phenomenon called a data race. A data race occurs when two or more threads access the same memory location concurrently. At least one of them is writing to it, and there is no synchronization mechanism in place. In our case, T1 is modifying the queue's internal structure by pushing, and T2 is modifying it by popping. The C++ standard library does not guarantee that these internal operations are atomic. Let's run it and see what happens. And as you can see, it crashes. Depending on your operating system and compiler, you might see a segmentation fault, a double free error, or the program might just hang indefinitely. Let's analyze why this specific crash happened. It's important to understand that queue push and queue pop are not single CPU instructions. They are complex functions that manipulate memory pointers. When the producer calls push, the queue has to allocate new memory for the node, then set the value and update its internal tail pointer to point to this new node. Simultaneously, when the consumer calls pop, it has to look at the head pointer, retrieve the value, then delete the node and update the head pointer to the next element. If these two operations happen at the exact same nanosecond, the internal pointers of the linked list or DQ that backs this queue get corrupted. The head pointer might end up pointing to a memory address that was just deleted by the other thread, or the size counter might get desynchronized from the actual number of elements. Thread 1 reads the current state of the memory to figure out where to write the new data. Before it can write, thread 2 comes in and changes that state. Thread 1, unaware of that change, writes its data based on the old information, effectively overwriting or corrupting the work of thread 2. This is undefined behavior. There is actually a second, more subtle race condition here, specifically in the consumer. Look at these three lines: the check for empty, the access to front, and the call to pop. Even if the queue's internal methods were individually thread safe, this sequence of logic is not. Imagine the queue has exactly one item. First, the consumer checks if the queue is not empty, which returns true. But at this moment, the operating system pauses the consumer thread and lets another thread run. That second consumer pops the item. The queue is now empty. Then our first consumer wakes up when it is already inside the if block. It tries to call queue.front. Because the queue is now empty, queue.front accesses invalid memory. The program crashes. This is often called a time of check to time of use vulnerability. The state of the system changed between the time we checked it and the time we used it. This demonstrates that we cannot simply check our way out of concurrency problems using if statements. The check itself is part of the race. We need a way to make the check and the action indivisible. We need to make them atomic. To achieve this, we need a mechanism that allows one thread to say, I'm working on this queue and nobody else is allowed to touch it until I am finished. This is called mutual exclusion, or a mutex. In the next section, we are going to modify this code to introduce mutexes. We will see how it fixes the crash, but we will see how using it natively introduces a massive performance penalty known as the busy wait. Now that we have established that our program crashes due to a data race, we need to discuss the solution. The fundamental problem we are facing is that two threads are trying to access the same memory address at the same time, and at least one of them is trying to write to it. To fix this, we need to enforce a rule known as mutual exclusion. Think of the mutex as a rule of ownership. To touch the queue, you must hold the mutex object. If the producer is holding it, the consumer can't have it. The consumer is forced to pause and wait until the producer is willing to let go. Let's go ahead and add the necessary components to our code. We need to include the header file and we need to declare a global mutex object that both threads can see. We have added the mutex header here. This is part of the standard library introduced in C++11. Before C++11, we had to rely on platform-specific libraries like POSIX threads on Linux or the Windows API, which made code non-portable. Now this works everywhere. So this mutex is global, so both threads can access the same instance. This is the most important rule of locking. You cannot synchronize two threads using two different locks. If the producer locks mutex A, it does not stop the consumer from locking mutex B. They must both try to lock mutex A to successfully block each other. Now let's apply this protection to the producer function first. The critical section is the specific block of code where the shared resource is being accessed or modified. You might have expected me to write something like mutex lock before the push and mutex unlock after the push. While that technically is valid C++, it is considered bad practice. Instead, I'm using std. This line is incredibly important, so let's break down what is happening here. This is a classic C++ pattern called RAII, or Resource Acquisition is Initialization. When we construct this lock object, the constructor immediately attempts to lock the mutex. If the mutex is already held by another thread, this line of code will pause. The thread will go to sleep and wait right here until the mutex becomes available. The real power of lockguard comes from what happens here, at the end of the scope. When the execution reaches this closing curly brace, the lock object goes out of scope and is destroyed. The destructor of std lockguard automatically calls unlock on our mutex. But why do we do this instead of manual locking? Imagine if q.push throws an exception, perhaps we ran out of memory. If we had written a manual mutex.unlock call after the push, that line would never execute, because the exception would cause the function to exit early. We would be left holding the lock forever, causing a permanent deadlock in our application. By using std lockguard, the compiler guarantees that the lock is released during stack unwinding, no matter how we leave this block of code. Now let's look at the consumer. This is where things get a bit tricky, and it's where many developers make their first mistake with concurrency. We need to decide where to place the lock relative to the while true loop. If we place the lock outside the loop, the consumer will grab the lock and hold it forever while it loops infinitely. The producer would never be able to get into push data. So we must place the lock inside the loop, so that we lock, do our work, and then unlock to give others a chance. Here is the updated consumer. Notice that in every single iteration of this while loop, we are creating a new lock guard. We acquire the lock, we check the queue, then we maybe pop an item, and finally, when we hit the bottom of the loop scope, we release the lock. Recall that in the previous section, we discussed the time to check to time of use bug. We were worried that the queue might change between checking empty and calling front, because we have wrapped this entire if block inside the protection of the log guard. We have made this sequence of operations atomic. To the outside world, checking the size and removing the element happens as a single invisible unit. No other thread can sneak in and modify the queue while we are inside this block, because they would be blocked waiting for the mutex we currently hold. Let's run the code now. As you can see, the crash is gone. The program runs as expected. We have successfully solved the data race and the memory corruption. The undefined behavior is gone. However, if you look closely at what the computer is actually doing, we have introduced a new, perhaps an even worse problem from an engineering standpoint. If you check your CPU usage, you might see it fluctuating or spiking. This is known as busy wait. The consumer is executing a tight loop, locking, checking, and unlocking repeatedly. This causes lock contention, where the thread creates unnecessary work for the operating system by constantly requesting access to the mutex. We are using CPU cycles just to check if work exists, rather than simply waiting for it to arrive. Let's trace the execution path of the consumer when the queue is empty. First it enters the loop, then it acquires a lock. Then it checks if the queue is not empty, but right now the queue is empty, so the condition is false. So it skips the if body. Then it hits the end of the loop, destroying the log guard and releasing the mutex. Finally, it immediately jumps back to the top of the while loop and repeats the process. It is doing this loop millions of times per second. So this is called a busy wait loop. The thread is technically working because it is executing instructions, but it isn't doing anything useful. It's just spinning, burning electricity, generating heat, and stealing CPU cycles from other threads that might actually have work to do. In a mobile application, this would drain the user's battery in minutes. In a server environment, this would cost you money on your cloud bill because your CPU utilization metrics would be artificially high. We are currently using a polling model. We are constantly asking, is there new data? What we really want is an event-driven model. We want the consumer thread to go to sleep, so to literally be removed from the CPU scheduler, until the producer wakes it up and says, hey, I just put something in the queue for you. The stud mutex is great for protection, but it has no mechanism for signaling or notification. It cannot tell a thread to wait for a specific condition. To solve the busy wait, we need a different tool from the C++ standard library. We need the stud condition variable. In the next part of this video, we are going to refactor this code. We will see how stud condition variable allows our thread to communicate, dropping our CPU usage to near zero while waiting and giving us the high performance, professional grade solution we are looking for. So we have secured our data against corruption, but we are paying a heavy price in CPU cycles. The consumer thread is always awake, checking an empty queue. To fix this, we need to change our approach from polling to signaling. A condition variable is a synchronization tool that allows threads to wait until a particular condition occurs. You can think of it not as a lock, but as a signaling notification system. Let's add the necessary components to our global scope. We have added the header and declared a global object called stud condition variable cv. Notice that unlike the mutex, the condition variable itself doesn't hold the data. It doesn't wrap the queue. It is simply a communication channel. Threads will use this object to send signals to each other. The workflow we want to achieve is the following. The producer will push data and then metaphorically speaking, ring the bell using this variable. The consumer will sit by the bell asleep and only wake up when it rings. Let's update the producer first, as it is the easiest part. We have added cv.notify1 immediately after pushing to the queue. Technically, you can call this function even after the lock is released, but calling it here is perfectly fine and often easier to reason about. What notify1 does is look at the list of threads currently waiting on this condition variable. If there are any threads sleeping, it unblocks one of them. If we had multiple consumers, we might use notify all to wake everyone up. But since we are just processing items one by one, notify one is more efficient. If no one is waiting, the notification is simply lost, which is fine. if the consumer is already awake, processing data. It doesn't need to be notified. Now we move to the consumer. This is where the logic changes significantly. Currently we are using std_logguard. However, std_logguard is a very simple, rigid wrapper. It locks on construction and unlocks on destruction. It cannot be unlocked manually in the middle of a scope. This is a problem for us. Why? Because if the consumer goes to sleep waiting for data, it must release the mutex. If it went to sleep holding the mutex, the producer would never be able to acquire the lock to push data and we would deadlock. Therefore, we must replace std_logguard with its more flexible sibling, std_unique_lock. Okay, we have swapped logguard for unique lock. Functionally, they start the same way. The constructor acquires the lock. However, unique lock provides the ability to temporarily unlock the mutex and relock it later. This capability is mandatory when working with condition variables. The standard library function cv.wait specifically demands a unique lock. This single line of code, cv.wait, is doing a tremendous amount of heavy lifting. Let's break down what happens inside this function call. When the code hits this line, three things happen atomically. The thread releases the mutex lock. This allows the producer to enter the critical section. Then the thread moves itself from the running state to the blocked or waiting state. It tells the operating system scheduler, do not give me any CPU time, I am asleep. Finally, when the producer calls notify1, the operating system wakes this thread up. It then immediately attempts to reacquire the mutex. Once it has the lock back, the function returns, and we proceed to process the data. Now you will notice I passed the second argument to the wait function, a lambda, or an anonymous function. This lambda simply checks if the queue is not empty. This is called the predicate. You might ask, why do we need a check here? If we woke up, doesn't that mean that there is data? The answer is not necessarily. This brings us to one of the most confusing concepts in concurrency. A spurious wake up happens when a thread wakes up from a waiting state even though no one called notify. This can happen for internal implementation reasons within the operating system or the threading library. It's like waking up in the middle of the night thinking your alarm went off, when it actually didn't. If we didn't have this lambda check and the spurious wake up occurred, our thread would wake up. It would then relock the mutex and try to call queue.front on an empty queue. That would crash the program. By passing this predicate, we are effectively telling the standard library to run a loop for us. Internally, cv.wait does something like this. First, it checks the predicate. Is the queue empty? If it is empty, it unlocks and sleeps. When it wakes up, whether from a notification or a spurious wake up, it logs the mutex and checks the predicate again. If the queue is still empty, meaning it was a spurious wake up, it goes right back to sleep. It only allows code execution to proceed past this line if the thread is awake and the predicate returns true. Let's run this optimized version. The output looks exactly the same as before. The functionality hasn't changed, but the engineering behind it has transformed. The CPU usage is now effectively zero. The consumer thread is sleeping until it is notified, rather than constantly checking the queue. This solves the efficiency problem completely. The consumer thread is now spending almost all of its existence in the blocked state, waiting for the operating system to signal. It only wakes up exactly when work needs to be done. This is an efficient, event-driven architecture. We have successfully built a thread-safe, efficient producer-consumer system. Looking at this concurrency demo.cpp file, well, it's getting a bit messy. We have global variables floating around, the queue, the mutex, the condition variable. This violates the principle of encapsulation. In a real project, you wouldn't want these implementation details leaking out into your global scope. So in the final part of this video, let's do a proper C++ refactor. Let's take all of these moving parts, the mutex, the condition variable and the queue, and let's wrap them inside a clean, reusable template class called ThreadSafeQueue. We will also discuss one final gotcha regarding exception safety when popping items. Let's take a look at the code. We have arrived at a solution that is technically correct and performant. However, structurally it leaves a lot to be desired. We are relying on global variables like Q, mutex and condition variables floating around in the global namespace. In a large codebase, this becomes quickly unmanageable. You can't have a global mutex for every single piece of data you want to share. We need to encapsulate this logic into a self-contained, reusable component. We want to be able to instantiate a ThreadSafeQueue just like we would a stud vector or a stud map. Let's clean this up by creating a template class. By making the class a template, the queue is allowed to hold integers, strings, custom objects, or network packets, without us having to rewrite the threading logic every time. Inside the private section, we have moved our three key ingredients: the standard queue, the mutex, and the condition variable. These are now member variables. This ensures that every instance of ThreadSafeQueue carries its own synchronization primitives. If you create 10 different queues, they will have 10 different mutexes, so they won't block each other. The push method is straightforward. It's almost a copy-paste of our previous producer logic. We take the value, log the mutex, move the value into the internal queue, and then notify waiting thread. Now, I want you to pay very close attention to the signature of this function, and we are passing a T reference. You might be wondering, why didn't we just write a pop function with a T return value? Why don't we just return the value directly like the standard stdqueue does? This is a subtle but critical design choice driven by exception safety. Let's imagine for a moment that we define this function as pop with a T return value. Inside that function, we would take the item from the front of the queue. We would call queuePop, which destroys the item inside the internal container. Then the function would attempt to return a copy of that item to the caller. Here is the danger. What if the copy constructor of T throws an exception during that return process? Perhaps the system is out of memory, or the object is complex and it fails to copy. If that happens, the function exits with an exception. But we have already called pop on the internal queue. The item has been removed from memory, but we have successfully deleted it from the queue. That data is lost forever. By passing a T reference into the function, we change the order of operations. First, we wait for the lock. Second, we assign the front element to the user's variable. If this assignment throws an exception, the stack unwinds. Then we exit the function and the lock is released. But crucially, we haven't popped the item yet. Only after the data is safely in the user's hands do we call queue_pop. This guarantees strong exception safety. No matter what happens, we never lose the data. Now look at our main function again. It is much cleaner. All the complexity of mutexes, locks and condition variables are hidden away. We just declare a ThreadSafeQueue, pass it by reference to our lambdas and call push and wait and pop. We have effectively extended the language. We built a new synchronization primitive that behaves correctly, handles concurrency safely, and optimizes CPU usage, all the while providing a safe, easy-to-use API. Let's run the program just to make sure it still works. And there it is, a fully functional thread-safe generic queue in C++. To recap what we covered today. We started with a crash caused by a data race. We fixed the crash with stud mutex, but it was inefficient because of busy wait. Then we optimized the performance using stud condition variable and stud unique lock. Finally, we encapsulated it all into a template class with exception-safe interfaces. If you got value out of this deep dive into concurrency, do me a favor and check out the rest of the channel. We are building a massive library of modern C++ programming content. Your support really helps keep it going.